Ever flick a light switch and wonder, like, how does that even work? How does it instantly flood the room with light?
Right.
Today, we are going deep into the world of electricity generation,
Oh, yeah.
from basic physics all the way to the power grid.
It's pretty fascinating stuff.
It really is. And we have some slides here to help us unpack this topic.
Excellent.
And I have to say, I'm already buzzing with anticipation.
Well, I think what's really interesting is how easily we take electricity for granted, you know? But when you understand how it's generated, it's actually a symphony of scientific principles and engineering, all orchestrated to power our modern lives.
Yeah, it's like a magic trick we perform every day without even realizing it.
Truly.
Our source material really emphasizes understanding the relationship between electricity and magnetism.
Right.
Different methods of generating those electrical currents and how they have practical applications that touch every aspect of our lives.
Yeah, absolutely.
So are you ready to kind of demystify this invisible force that keeps our world running?
I'm ready. Let's do it.
All right, let's dive in. So to truly grasp this magic,
Yeah.
we need to start with Faraday's law.
Ah, yes, Faraday's law.
It sounds a bit like a legal thriller,
It does, doesn't it?
but I am intrigued, so lay it on me.
Okay, so imagine a simple coil of wire moving through a magnetic field.
Okay.
That movement, that change in the magnetic field, creates something called an electromotive force.
EMF.
EMF, exactly, or EMF. And that EMF drives the flow of electrical currents.
Wait, so it's all about magnets in motion? So like if I wave a magnet around a wire, I'm creating electricity.
In essence, yes, you're tapping into the same fundamental principle that powers those massive generators and power plants.
Whoa.
There's a lot more to it, of
Okay.
course, but that basic interaction between magnets and conductors,
Right.
that's at the heart of electricity generation.
That's mind-blowing. It's like we're harnessing an invisible force field
Yeah.
to power our world.
It really is.
Our source material also mentions Faraday's constant,
Okay.
and that involves a ridiculous amount of
On
electrons.
a lot of electrons.
So how does that fit into all of this?
Yeah, so Faraday's constant basically dives into what electricity is made of, electrons.
Okay.
This constant tells us the precise amount of electric charge carried by 1 mole of electrons, which is a whopping 96,485 coulombs per mole.
That's a big number.
It's a huge number. To put that in perspective, 1 mole of anything is roughly 602 sextillion things.
Okay, my brain's already hurting. That's too big.
It's massive. It's hard to fathom.
Okay, so we're talking about a mind-boggling number of electrons zipping around,
Yeah.
carrying this charge.
Yeah.
That powers everything we do.
Hmm?
But why should I care about this massive number? Does it actually impact me?
It totally does, especially when you think about batteries and
Okay.
electric vehicles.
All right.
You see, that huge quantity of electrons, as defined by Faraday's constant, it impacts the storage capacity of batteries.
Gotcha.
The more electrons a battery can store, the longer it can power a device.
So that's why they're always trying to develop new battery technologies.
Exactly, to pack in more of those little guys.
More electrons, more battery life. Yeah.
Exactly.
Okay, so Faraday's constant isn't just some abstract concept out there.
It's a real thing.
It's tied to how long my phone stays charged or how far an electric car can drive.
Exactly.
That's pretty cool. That makes a lot more sense.
It's a practical application of this.
All right, so how do we actually get from these basic principles to those massive power plants that we rely on?
Well, that's where generators come in.
Yeah.
They are the workhorses of power generation. Essentially, generators are machines that convert mechanical energy into electrical energy, all thanks to Faraday's law.
So we're talking about wind spinning a turbine or water flowing through a dam and converting that into electricity using these generator things.
Exactly. And these generators come in all shapes and sizes, from the tiny ones in your phone that convert the vibrations of your voice into electrical signals,
Oh, wow.
to the massive ones in power plants that light up entire cities.
It's amazing the scale of it all.
It really is, yeah.
Our source material also highlights practical applications across different sectors, like renewable energy, which is obviously very relevant these days.
Absolutely.
So what are some of the ways that generators are used in these different sectors?
Well, generators are essential in traditional power plants that rely on those fossil fuels, but also in the rapidly growing field of renewable energy. For example, wind turbines use those massive blades to capture the kinetic energy of the wind and spin a generator inside, converting that mechanical energy into electricity. And hydroelectric dams use the force of falling water to spin turbines connected to generators,
Harnessing the power of gravity.
harnessing the power of gravity to generate clean energy.
So whether it's wind, solar, even geothermal generators play a key role in converting those natural energy sources into usable electricity.
That's right, yeah.
That's incredible. Are generators only found in these large-scale settings? Or what about smaller everyday applications?
Oh, generators are everywhere. Think about backup generators people have for power outages.
Oh, right, yeah.
They kick in when the power grid is down, providing a localized source of
It's
electricity.
what keeps essential appliances running.
Exactly, yeah.
Oh, okay, that makes sense.
They're also crucial for powering tools and equipment in places without access to the grid.
Like construction sites or more remote areas.
Exactly, yeah.
So we've got these small-scale generators providing backup power, and then these massive ones in power plants,
Right.
harnessing all sorts of different things
Yeah.
to create the electricity that powers our world.
It's a global network of energy conversion happening all around us.
Wow. Okay, that brings us to AC and DC.
Yes, ACD.
I've heard those terms thrown around, but I'm honestly not quite sure I get it.
Okay, sure.
Can you break it down for me?
Absolutely. Direct current, or DC, is the type of electricity produced by batteries and solar cells,
Okay.
and it flows in one direction.
Like a steady stream of electrons.
Yes, like a river flowing downstream.
Okay, I can picture that.
Yeah.
What about alternating current?
Alternating current, or AC, is the type of electricity that powers our homes and businesses.
Right.
And unlike DC, which flows in one direction, AC periodically reverses its direction, creating this fluctuating flow of electrons.
So it's not a steady stream.
Not a steady stream, it's more like a wave in the ocean.
Okay.
Constantly rising and falling, switching back and forth.
Okay, so DC's like a river.
Yeah.
And AC's like the ocean.
That's a good way to think about
Okay,
it.
I like that analogy. That makes sense. But why is this distinction important?
Good question.
And why do we use AC for our power grid if it's constantly changing direction? Wouldn't that make it less reliable?
That's a great question, and it leads us to the transformer.
Okay.
The dynamic nature of AC, its ability to change direction, makes it much easier to transform,
Okay.
meaning we can increase or decrease the voltage using these devices.
Transformers. Like the robots in disguise.
Not quite, but they are pretty cool.
But seriously, why is this ability to transform voltage so important?
It comes down to efficiency and safety.
Okay.
To transmit electricity over long distances without losing too much energy, you need to use extremely high voltages.
Like hundreds of thousands of volts?
Yeah, exactly. But we certainly don't want that coming into our homes right now.
Definitely not. That would be pretty dangerous.
That would be incredibly dangerous.
I wouldn't want to plug my toaster into that.
No, not at all. So these transformers act as intermediaries,
Okay.
stepping up the voltage for transmission
Right.
and then stepping it back down to a safe level before it reaches our homes.
So they're like, I don't know, the bouncers of the power grid, making sure everything's running smoothly and safely.
I like that, the bouncers of the power grid. Yeah, they're crucial for making electricity safe and usable in our daily lives.
Okay, so they're more like the unsung heroes.
Well, unsung heroes.
That's pretty cool. So we've gone from magnets and wires to generators and transformers,
Yeah.
all working together to deliver this invisible force safely to us.
A symphony of technology.
But I'm still a little fuzzy on how the electricity actually gets from the power plant to my house.
Okay.
Is it just like a direct line?
Not quite. The journey of electricity from the power plant to your home is more like a relay race, involving a complex network of transmission lines, substations, and distribution lines.
All making up what we call the power grid.
Precisely, the power grid.
It sounds vast and complex,
Oh, it is.
and I'm eager to learn more about how it works,
Yeah.
but I think we'll have to save that for next time.
Part 2.
But for now, I think we've covered some really electrifying ground, from Faraday's law to those massive generators and transformers.
I think so.
What stands out to you so far?
It's really amazing how these scientific principles are woven into our everyday lives, you know?
Right?
We just flip a switch and we don't even think about it.
Right. We take it for granted.
But it's a symphony of physics and engineering that has totally revolutionized our world.
It's like we've been living in a world of magic without even realizing it.
It really is, yeah. Magic and science all rolled into one. It really is amazing, a testament to human ingenuity, our
Yeah.
ability to harness the forces of nature to power our modern lives.
It is. It is. And speaking of harnessing, remember those electrons we talked about?
Oh yeah, those tiny little guys.
They're not just passively sitting in wires, are they?
No, they're not.
So how do they actually move? Do they flow like water in a pipe?
Well, That's a common analogy, but it's not quite accurate.
Okay.
Electrons don't actually zip through wires at lightning speed.
Right.
Instead, it's more like a chain reaction.
Okay.
One electron bumps into another, transferring energy along the way.
Gotcha.
It's less about physical flow and more about a transfer of energy.
So like a microscopic game of dominoes,
Exactly.
creating a wave of energy that goes through the wire.
Yeah, that wave of energy is what allows us to power our devices, light up our homes, and even run massive industrial machinery.
All thanks to those tiny electrons.
Yeah.
That's wild. Okay, let's zoom back out to the bigger picture.
Okay.
We talked about the different types of power plants, from those traditional fossil fuel ones to renewable energy.
Yeah.
Our source material emphasizes how these diverse approaches all rely on generators,
Right.
which convert various forms of energy into electricity.
That's right. Yeah. Generators are at the heart of it all, regardless of the energy source.
So whether it's burning coal or harnessing the wind, it all comes down to spinning those turbines.
Yeah, it's all about that mechanical energy to electrical energy conversion.
It's fascinating how diverse their applications are. So can you give us some specific examples? How are they used in these different sectors?
Sure. Let's start with residential backup generators. You know, those systems that kick in during a power outage?
Yeah. Those are lifesavers.
They provide that lifeline, keep essential appliances running.
They're like the superheroes of home electricity,
Exactly.
keeping things going when the grid takes a hit.
Absolutely. They swoop in to save the day. But on a larger scale,
Right.
generators are the workhorses in industrial settings.
Okay.
They power heavy machinery, manufacturing processes.
Right. So they ensure things run smoothly.
Continuous operation even when the main power is interrupted.
Yeah, so factories, construction sites all rely on them.
Yeah, even mining operations rely on them.
It's amazing how much our industrial capacity hinges on those generators.
It is.
But it's not just keeping the lights on. Our source material mentioned transportation as well.
Transportation, right. Generators are vital in vehicles, airplanes, even ships.
Oh, wow.
Providing power for electrical systems, lighting, navigation.
So our cars rely on these principles of electromagnetism.
Oh yeah, for smooth and safe operation.
I never really thought about that. It's crazy how integrated they are.
They're everywhere.
All right, before we move on, I want to go back to AC/DC.
Okay, back to AC/DC.
We talked about the differences, but why is AC the preferred choice for power transmission? What makes it so special?
It all boils down to transformers and how AC interacts with them.
Okay.
Remember, AC can be stepped up or down in voltage using those transformers.
Right.
And that ability is crucial for efficient power transmission over long distances.
Higher voltage means less energy loss.
Exactly. Less energy wasted as heat.
But we need lower voltage for safety in our homes.
Right, so it's a delicate balance.
So AC lets us adjust the voltage to meet those different needs.
Exactly. By stepping up the voltage for transmission, we minimize energy loss, which is super important for efficiency.
And then we step it back down to a safe level.
Right, before it goes to our homes and businesses.
So AC wins the battle of the currents
You could say that, yeah.
because of how we can manipulate it with transformers.
Precisely. It's all about that flexibility. And that brings us to another interesting aspect of AC. It's sinusoidal waveform.
Sinusoidal waveform. Okay, can you break that down a little?
Sure, imagine a wavy line
What?
that represents the voltage of AC over time.
Okay.
This wave-like pattern is called a sine wave,
Got it.
and it shows how the voltage fluctuates between positive and negative values.
So it's like those heart rate monitors you see in hospitals. Up
Yeah.
and down, up and down.
Yeah, that's a good visualization. But this wavy nature of AC, it's not just a random pattern.
Okay.
It's crucial for how AC is used, especially for powering motors.
Wait, so the wavy thing makes our electric motors spin.
It's a key part of it.
Whoa. Electric motors rely on magnetic fields to generate that rotational force.
Okay.
And the fluctuating magnetic fields created by AC, thanks to its waveform,
Right.
they're perfect for interacting with the motor's components.
So it's all connected.
Exactly.
So AC's waviness isn't just a quirk, it's like a superpower.
It's what makes it all work.
That's so cool. But let's not forget about the power grid itself.
The unsung hero.
Yeah, the unsung hero. We've talked about the journey of electricity, but the power grid is what makes it all possible.
Right. It's like the nervous system of our modern world.
Connecting everything.
It's a remarkable feat of engineering, constantly balancing supply and demand.
Okay, I'm hooked. Walk me through how it works. Where does the electricity go after the power plant?
It starts with those high-voltage transmission lines.
The superhighways of electricity.
That's a good way to put it. They carry electricity over long distances
Right.
at super high voltages.
To minimize energy loss.
Exactly. But we can't have those crazy high voltages coming into our homes.
Mm.
That's where the substations come in.
Right. Substations are like the off-ramps.
They slow things down?
They step down the voltage to a safer level
Okay.
before it goes to neighborhoods and businesses.
Gotcha.
So after the voltage is stepped down, it travels along distribution lines.
The local roads.
Yeah, reaching individual homes and businesses, powering our lives.
It's pretty amazing when you think about the scale of it all.
Oh, it's a complex system.
So well choreographed.
Yeah, from power plants to substations to our homes, all orchestrated by this network.
It really is a testament to human ingenuity.
Yeah, our ability to harness and control the forces of nature to meet our energy demands.
This deep dive has given me a newfound appreciation for the invisible force that powers our world,
Me too.
from those tiny electrons to the vast power grid.
Yeah, it's an incredible story.
But I have to ask, with the rise of renewable energy, how is the power grid adapting to these changes?
That's a great question and a big one.
Yeah.
The power grid of the future is going to need to be more flexible, intelligent, and resilient to handle the increasing integration of these new energy sources.
Okay.
But for now, let's just take a moment to appreciate the marvel of engineering that we have today.
I'm with you on that one.
It delivers electricity to our fingertips every single day.
It's amazing.
It really is.
We totally take it for granted.
We do.
Well, this has been an electrifying journey.
It has been fun.
Before we started this deep dive, I thought I kind of knew how electricity worked.
Yeah.
But now, after seeing how everything works together,
Right.
all the physics, the engineering, the power grid,
It's complicated.
I am blown away.
Yeah.
What about you? What's been the most surprising thing for you during this?
I think for me, it's the sheer scale of it all. From those tiny electrons to those massive power plants.
Right.
It's mind-boggling how it all works together.
Yeah, it really highlights how interconnected our world is. As we wrap up this electrifying journey, what about the future of electricity? Our source material mentions some challenges and opportunities with renewable energy.
Yeah, definitely. It's a big question.
So what are your thoughts?
As we move towards things like wind and solar, the power grid's going to need to be way more flexible.
Okay.
Those sources are intermittent.
They depend on the weather.
Exactly. They generate power when the wind's blowing or the sun's shining.
So that's a challenge.
It is, because the traditional power grid was designed for more stable and predictable sources.
So how do we integrate these variable renewable energy sources into the grid? What needs to happen?
Well, one thing is we need to invest in energy storage.
Okay.
Things like batteries, pumped hydro.
Okay.
They can store excess energy and release it when needed.
So it's like creating a buffer.
Exactly. Smooths out the variability, makes them more reliable.
What other innovations are out there?
Smarter grids are a really exciting area.
Okay, smart grids.
They use sensors and data to monitor and control the flow of electricity in real time.
So it's a more dynamic grid.
Exactly. It can anticipate fluctuations and adjust automatically.
And it can even help consumers manage their own energy use.
That's right.
So it's not just about hardware, it's about software and data, too.
Absolutely. Technology is a big part of it.
And we can't forget about consumers.
Right. Of course not. We all have a role to play.
Making choices that support renewable energy.
Installing solar panels, choosing energy-efficient appliances.
Being more mindful.
Yeah, every little bit helps.
This deep dive has been eye-opening.
It has been fun to explore.
Not just about how electricity works, but also about the challenges and opportunities ahead.
We've only just scratched the surface.
Yeah, we have. But knowledge is power, right?
Absolutely.
Understanding these things helps us make more informed decisions.
As individuals and as a society.
So next time you flip that light switch, think about the incredible journey that electricity has taken to get there.
From the power plant to the grid to your home.
And consider the role you can play in shaping a more sustainable future.
Keep asking questions.
Keep exploring.
And stay curious.
Until next time, stay charged up.